Welcome, this is the Further Math Support Programme in Wales, providing you with a work solution to the June 2018 Higher Unit 2, so that's the calculator paper, question 19. The topic is geometry, so sine rule, cosine rule and the circle theorems. But note, if you are sitting the exam in summer 2022, many of the circle theorems are not on the paper. So in particular, the alternate segment theorem, which occurs here, is, in my reading, not on the paper. So here is the sine rule that we all know and love. What does it mean? What's written here is what you get on the front cover of the exam paper, but in words what it means is for any triangle, if you choose any of the three sides and divide them by the sine of the angle that they're facing, for that triangle you'll get the same value. Now, another comment, we actually only ever use one bit of it at a time. We set up an equation so we could ignore the c over sine c bit, and the equation we set up, we'll just use the first bit of it. We can use this one equation if we're going to get one unknown, which means we need to know three of the other bits to use it. So we could know two of the angles and a side, or we could know two of the sides and an angle. But in either case, in order to be able to use the sine rule, you're going to need to have an angle you know opposite a side you know. So if you don't have that, you can't use the sine rule. Finally, a good thing to know is that it's also true if we turn each of the fractions upside down. In particular, if we're trying to calculate the angle, sometimes we might start with it in this form because there's a bit less rearrangement to do. So that's handy to have up our sleeve. If we start in the other version, it will still give us the right answer, just maybe more rearrangement. And here we go. Here is the cosine rule as it appears on the front of the paper. What can we say about that? Well, what does it mean? It means that in a triangle, if we choose any side, then the square of its length is equal to the sum of the squares of the other two sides' length minus their product times cosine of the angle between them. If the angle is 90 degrees, then cosine would be 0 and we'd recover Pythagoras. But if we've got a right angle, we don't use the cosine rule. We could go direct to Pythagoras and use it. It works in some situations we can't apply the sine rule. So the general setup is that in any triangle there are 6 bits of information, 3 angles, 3 sides. If we knew just the 3 angles, we couldn't say anything about the side length, but if we knew 3 bits of information, including one of the sides, then we can work out everything else. We can work out the other side lengths and angles. Now, if we don't have a side opposite an angle, then we can't use the sine rule, but we can use the cosine rule. So if we've got 3 bits of information, including a side, and we can't use the sine rule, then the good news, we can use the cosine rule to get everything else that we need. Final comment, we can rearrange it, the cosine rule, to make cosine, in this case cosine A, the subject of the formula. Why would we want to do that? Well, it's useful if we're trying to calculate the angle A. It's sometimes useful to start here, and just like the rearranged form of the sine rule, if you start with the other form and rearrange it, that will be fine as well. So it's a matter of personal taste, personal preference. So for circle theorem material, first note that if you're sitting this in summer 2022, that have a look at the adaptations, because this theorem is not on the paper, but it's a really important bit of math, so it's good to know, and it's handy and surprising. So this one is that if you've got a circle, the angle at the center is double that of a point at the circumference, and that means from that actually that's true for any point at the circumference. So all points on the circumference subtend, the angle subtended is the same, and it also gives you the result about the angle in a semicircle being a right angle. Another important circle theorem, again this result will not be on the summer 2022 GCSE papers, is the alternate segment theorem. So what's that saying? You've got a circle. If you've got a tangent like CD here which touches a circle at C, you've got a chord BC and the angle between the tangent and the chord is X. That will be the same as the angle subtended by the chord BC in the segment opposite the original angle, so the so-called alternate segment. So that is used in the question that's coming up. It's not on the summer 2022 papers. And you can derive it from the result we just saw previously about there being double the angle at the center of the circle, and you'll also need the fact that the tangent is perpendicular to the radius. So here we go. Here is the question. It says BC. So let's find out. BC is a tangent to the circle at this point E here, as shown below. EC is 8 centimeters, so that's that bit. AC is 11 centimeters and DCE is 31 degrees. And the first thing they ask us is calculate the length of a E down here. So what's our thinking? Well, our thinking, the first bit is what I've just shown as I read. So in the question, you're going to read some information, you're going to have a diagram, and you need to match them up. So which lengths and angles on the diagram have we been given? So it talked about EC being 8 centimeters. So I'm just going to label things with numbers. I'm going to do the calculation with numbers, and I'm going to put the units back in at the end. EC is 8. AC is 11, DCE they've labelled for us, the angle 31 degrees. So we've got the information. Then it says calculate the length of AE. So we need to say, okay, so what are they, we know what they've told us and what it means. We now need to know what are they asking, and they want this side here on the left, AE. Next natural question is, okay, how are we going to do it? What tools can we use? So of all the things we know. Now, a good question to ask is, in these geometrical problems, is, are there any obvious right angles? If there are, we can use Pythagoras and SOHCAHTOA. If there aren't, we can't. Now, there aren't any obvious right angles, so we're not going to use that. And we're going to have to use the sine rule, cosine rule, or a circle theorem. So again, we say, can we use the sine rule? Remember what we said, the key thing for the sine rule is that you need an angle. We know an angle, but it needs to be opposite a side we know, and we don't, so we can't use the sine rule. Can we use the cosine rule? Yeah, we've got 3 bits of information, we can get going, so that sounds good. Circle theorems, well, this is the setup for the alternate segment theorem. This angle here is going to be the same as this angle up here on the left. However, they're asking us for a length, so that's not useful. We perhaps just note it and think, maybe it will come up later. Knowing the tricksy examiners, they've probably set this up deliberately. So we can say the sine rule won't work, cosine rule will work, and the alternate segment theorem may be handy later. Let us do that then to find the length. So here we go. Let's apply the cosine rule. So in this triangle, we know that AE squared is equal to the sum of the squares of the other 2 sides minus twice their product times the cosine of the angle between them, 31. And then it's a case of simplifying the right-hand side, or we can type it direct into our calculator. At some point, we're going to need to use our calculator. So let's do it here. And we get something close to 34. I've written out it several decimal places, 6 decimal places, but in fact I'm just keeping it in the calculator. So I'm keeping the full precision in the calculator and taking the square root to get the value. Again, I've listed it to 3 decimal places there, but I might give the answer to 2 or even 1 decimal place. So we've got the answer. A thing which we always try to do as mathematicians is check it if we can. Sometimes we can check it precisely. We can't in this case, but at least we can ask, is it reasonable? So mistakes are a way of life for the mathematician like we are. And we just need to get rid of them or try and avoid them. So is this reasonable? Now it says diagram not drawn to scale, but we can see it's not bad because that does look about like 30 degrees. And if we look at the side length, 11 is about, well, 1.5 times 8, a bit less than that, and that's looking reasonable. So we're saying, could we believe this length to be 5.8? And I think we can. I mean, had it come out, the answer come out as 11, we would have been a bit worried. At least we would have checked our working, or even 8, it would be a bit surprising. Similarly, if it was 0.01, or certainly if it came out as negative, we'd be checking our working again. But that looks reasonable, so we can smile and move on to the next part of the question. So here is the second part of the question, and the setup is the same, except we now know the length of this side. As I said before, I've got it on actually in the calculator to full precision. I've stored it perhaps in memory to pull it up when I need it. And now it says calculate the size of CED. So which angle is that? It's this one at the bottom here. So what is our thinking process then on this one? So we've identified which angle, what we need to calculate. We know what we know. Our next, I've highlighted it there, our next question then is what tools are we going to use? Now we've already said whether there are right angled triangles. But now we're talking about an angle, in particular we're talking about this angle, we can directly apply the alternate segment theorem. There we go, because maybe it's going to be easier to calculate this angle here up the top. So it gives us options. Now, it's not obvious. If we want to calculate, let's just think about this. If we want to calculate this angle at the bottom, then this triangle CED is a bit information poor, as in we've got one side and one angle, and we need 3 bits of information to get going. So in particular, we don't have enough to use sine or cosine rule. So let's go back to what we were saying. Well, alternate segment theorem may help us, because if we aim for this triangle, we do have plenty of information, because on the triangle AEC we've got 3 side lengths and we've also got an angle. Now, given we've got an angle opposite a side we know, we can use the sine rule, because what we can say is this, well, we're aiming for an angle, so we might say the sine of this angle 31 over 5.843 is the same as the sine of this angle up here, angle A over side length A. So that looks like a plan that will work. So let us try that on the next slide. So here we go. Sine of CAE over 8. That's just what we said previously. So sine of this angle over the side length opposite, and is equal to the sine of this angle over the side length opposite. Again, I say I've stored this value in the calculator. When I come to use it, I'm going to use the full calculator value, not my short version here. So carrying on down, multiply both sides of our top equation by 8. Then on the left, we're just left with the sine of the angle we're interested in. And we've got some calculation on the right. We can type that into our calculator and get a precise answer. Then we can take the inverse sine of both sides to give us 44.8 and a bit more information. Okay, that is good, because now we need to finally close out on the question by using the alternate segment theorem and saying that this angle we've just calculated is equal to the angle that we were asked to calculate. So let us do that. So by the alternate segment theorem, CED, what we wanted is 44.8. And again, we say, is that reasonable? We know this diagram's not drawn to scale, but it's at least plausible. So if the angle had been greater than 90, or if it had been really, really small, we would have wanted to check our working. But that looks like the right sort of angle, so we're happy with that. Okay, we've actually finished the question now. We've completed it. We're done. But could we have done it in a different way, this second part? And the answer is yes. We said there was plenty of information on this triangle. We've actually got 4 bits we've got 3 side lengths and an angle. We can use the cosine rule if we'd like. So let's find the angle top left, this one up here, using the cosine rule, and then we'll use the alternate segment to say it's the same as this one again. So let us do that. We're using the form that I mentioned earlier, where we start with the cosine of the angle expressed in terms of the side lengths. If you want to start with the classic form on the front of the paper, by all means do so, and then rearrange it to find the angle. But there we go, we've got the cosine of the angle. We evaluate the right hand side using our calculator, and then we take the inverse cosine of both sides to get us an angle. And the rest is going to be the same as we did previously. Using the alternate segment theorem, CED is 44.84. So we'd perhaps state that. And then finally, we also check plausibility if we're doing it this way as well. Great. Well done. We're done. But there's more. What about if the question wasn't exactly as they wrote? Because we know that if you set a GCSE paper, it's not going to be exactly the same question. How could we change this slightly? So I've changed it slightly. What I've said is we've got the same length, 8 centimeters for the EC, but what about if we instead knew this angle at the top, and we've still got 31, and what about if they asked us to calculate the length of DE? So let's label up the bit that we want to know. So that is the bit we're after. How do we solve it? Well, we're thinking about it. We're thinking, this is the alternate segment theorem again. So DEC is going to be 44. That would enable us to get the angle at the top here, EDC. And then we've got an angle opposite a side, and we've also got this angle. So we should be able to use the sine theorem to get our unknown side. Let's just check that does the job. So I've just highlighted the alternate segment theorem. So what we know is DEA is 44, so we can pop that in there. And the sum of the angles in the triangle is 180. So if we subtract 31 and 44 from 180, we get 105. So we can pop that in as well. And now we're in the position to use the sine rule. So let us use the sine rule on triangle DEC. We know that side length DE we're after over the angle opposite 31 degrees is side 8 over 105, sine of 105. We can rearrange that by multiplying both sides by the sine 31. So we just get DE on the left side, and we get this expression on the right, which we can use our calculator to evaluate. So we get 4.26565 and so on for the side, and then we round it this time to 1 decimal place. We look at it, say, do we believe that? Yeah, that looks plausible length. Again, if it was 107, we would, or negative, we would check our calculations. There we go. So that was a work solution by the Further Maths Support Programme in Wales of the June 2018 Higher Unit 2 GCSE paper, and we were going through question 19, which was on geometry using the sine rule, cosine rule and circle theorems.